All right, now let's continue our discussion in chapter 4. Last time we talked about the additive model, which states that each cell entry is equal to the grand mean plus the row effect and plus the column effect. However, I want to mention that this is only a model and not necessarily everything would follow this additive model. Or in other words, in a real life data, the cell entry is not necessarily equal to the grand mean plus the row effect and plus the column effect. And this equation is only true when the data follows the additive model perfectly, which may or may not be the case. And for example, in our next example, by the way, the next example is about half a century old. So in old days, if you buy a car, the cars are super cheap, and you can choose to buy a radio, you can choose to add a radio, or you can choose to say no to a radio, and also you can choose to add a heater or choose to say no to a heater. So suppose that you want to add a radio that costs an additional $50, a heater is 100, and you can choose to add either one of these two or both or none of them. And well, all these conditions should imply it's an additive model. However, the dealer decides to give a discount of $20 if you choose to buy both. So here you can have a heater. You can say yes or no, and now you can have the radio. You can also say either yes or no, and now this should give us a table, a 2x2 table, and that divides everything into 4 categories. So you can say yes to either one of these two or both of them, and you can say no to either one and both. So here, if you buy none of them, then of course you pay additional $0. If you buy just the heater but not the radio, so you say yes to the heater, no to the radio, you can pay additional $100. And if you buy just the radio, not a heater, pay $50. And if you buy both, supposed to pay $150, but you get a $20 discount. The 20% discount. 20% of $150 is $30, so you would end up paying $120. So in order to understand the data, let's calculate the grand mean. The grand mean is calculated by adding all those numbers, 120 plus 50 and plus 100 and plus 0 divided by 4. So all these numbers added together divides by 4, and you're going to get 270 divided by 4. So this number will be, I don't know, 67.5. So on average, you're going to pay $7.5. And also we can calculate the mean of each column. For example, the first column mean, 120 and 100 is 110 is 110. We just add these two numbers, divides by 2. And similarly, the next column mean is 25. It's 50 plus 0, and whole thing divides by 2. Now you can calculate the column effect. In this case, the column represents the heater, yes or no. And the column effect is calculated by using the column mean minus the grand mean. So here, the first column mean is 110 minus the grand mean is 67.5. So it's 1110 divides by 110 divides by, minus 67.5. So you're going to get 42.5. So 42.5 is how much is the column effect. And similarly here, for the second column, you use 25 minus 67.5. You get a negative number, negative 42.5. So this is the column effect. And you can do the same thing with the rows. So let's calculate the mean of each row. The mean of 120 and 50 is 85. Add these two numbers and divides by 2. And also the next row has the mean 50. It's 100 plus 0 divides by 2. And then we can also calculate the row effect. And here the row effect is calculated by using, again, the row mean 55 minus grand mean 67.5. So you can get 17.5. And finally, 50 minus 67.5 will get you negative 170, 17.5. So this is the row effect. Now, let's take a look at entry and see how we can estimate each entry by the grand mean and the row effect and the column effect. I'm going to change my color a little bit. I'm going to use this nice orange color. Let's study this entry right here. So here, this entry, and firstly, we're going to use an additive model to estimate. So the estimate by the additive model works like this. Assuming that everything follows the additive model, and then we're going to start from the grand mean, and then plus the row effect, and then plus the column effect. So here, the grand mean is 67.5. And then because it's in the second row, the column effect or the row effect is minus 17.5. So it's minus 17.5, you get 50, and then plus the column effect, which is 42.5. So it's 42.5 if you do the math, and you're going to get $92.5. So in other words, the additive model predicts that you're going to spend about $92.5 on this entry. That's not the same thing as the real reality, which is normal because after all, we're only estimating this using the additive model. I'm not saying this data set follows the additive model. Actually, it doesn't because of 20% discount. So we can calculate the residual. The residual is given by a subtraction of the actual number, which is 100, minus 92.5. In this case, is equal to 7.5. So what the 7.5 tells you is that in reality, the price is $7.5 higher than what this model predicts. So I would encourage you to pause the video now and try to do the same thing with the other three entries and make sure that you practice it before continuing the video. And you should get the same estimates as here, as well as all those residuals. All right, I trust that you have paused the video and practiced by yourself. It should take a couple of minutes. If you get a correct answer, that's great. If not, you can watch this video again and then try to follow exactly the same step as I did, and hopefully you get the correct answer. But now let's move on. And here, let's go back to our smoking example. This is the formal analysis of the smoke puff. So here, what we could do is to just analyze the raw data. That's perfectly fine. There's nothing wrong with it. However, there is something that's even tricky, even more trickier, and to make it a little bit more convenient. And the observation is that most of the data points, it will be 6 point something. Yes, I know there is 7.0, 7.2, that's 5.8. However, what we can do is if we can just subtract every number by 6. So what we're going to do is we can just make the data set has some smaller numbers. So instead of 6.2 as the first number, we're going to have 0.2. Instead of for example, instead of for 7, we're going to have for 1. Instead of for 5.8, we have negative 0.2. This is because 5.8 minus 6 is negative 0.2. And then what we can do, which I will be doing, I will not be doing it here by hand. I encourage you to either try it by hand, or if you like, practice this with R. Remember, we talked about R code for matrices in an earlier video. Make sure that you find the R code, and you can actually go back to the previous slides and find the R code for a matrix. And then you can calculate the grand mean. In this case, it's approximately 0.38. So which means for the raw data, the grand mean or the average of the pH value is approximately 6.38. And then we can also calculate the column mean of each columns. In this case, the column mean is 0.08. The next one is negative 0.02. And this one is 0.76, etc. You can also calculate all the row means. And from the column mean, you can calculate the column effect by column mean subtract by the ground mean. So for example, right here, you get 0.08 minus 0.38, that's negative 0.3. And negative 0.2 minus 0.38 is negative 0.4, etc. And here, after you do this, you can also calculate the residuals. You can find that the residual of our numbers are mostly, or all of them are non-zero, which means the additive model does not follow. I mean, the data does not follow the additive model perfectly, which is fine. And the residuals tell you how far away is the actual number from the model. So again, the ground mean plus the row I effect plus the row column J effect will give you an estimate, and the residual is calculated by the cell entry, which is the actual number minus the estimate. And well, why do we use this two-way table? Like, why do we just use this row mean and column mean, and as well as the ground mean to represent the data? First of all, for R by C table, we can summarize. We should have R times C numbers. That's usually big. If R and C are both big, R times C is even bigger. But instead of using these big numbers, we can use R plus C plus 1 numbers to summarize the data. And why is that number? Because we have R rows, C columns, we have R row means, and C column means plus 1. What is 1? 1 means the ground mean. So we use this R plus C plus 1 numbers. So for example, if R is 12, we have 12 rows and 10 columns. We should have 120 data points. But if you do R plus C plus 1, you only get 23. So that's quite a decrease of the data size. We can make the data set much smaller. And also the additive structure offers a baseline against which we can measure the interactions between the variables and test how the variables interact with each other. Let's take a look at the homogeneous table. And suppose there is a boring two-way table that every measurement is the same. Every measurement is the same. And then we're going to do an additive analysis. Well, this is basically everything is the same. You can maybe assume everything is 5 or everything is 7. And then let's say everything is 5 for simplicity. And then, of course, the ground mean is also 5. Every row mean is 5. And the residual of the row effect is always be 0. The column effect is 0. Residuals always be 0. So this is basically an example of perfect additive model. It's quite a trivial one, because everyone is the same. And more generally, when the additive model holds with the 0 residuals, and then we can perfectly represent the R by C table and by R row effects, C column effects, and the ground mean. What I mean by that is if the data set follows the additive model perfectly, then we can use only the row means, the column means, plus the ground mean to represent the whole data. You can recover the cell entry. Every cell you can just calculate by the estimate here, because assuming that the model is perfect, and then this residual will be 0, so the cell entry will be equal to the estimate if the residuals are all zeros. Of course, this may or may not be true in reality. Another thing we can do is to look at the model with one wild observation. What is that? Well, everyone, look at this data set. Everyone is 0 except for one entry, that is 1. Well, why do we have a model like this? Well, for example, you can think about the COVID testing. Most people would be tested negative, but maybe there's one positive people. So that person is sitting right there. And then what you can do is do the calculation of the ground mean. You can do the column mean. You can do the row mean, the row effect, and column effect. I encourage again you to pause the video and complete this calculation by yourself. This one, right? Sorry, it's actually this one right here. Pause the video and finish the calculation. And now when you calculate the residuals, what you will observe is that there is one residual that's unusually unusually big. This is 0.6. And that one is the unusually big residual that tells you that is where you observe the most departure from the model. That is where you find one wild observation. This observation is just different, so different. All right, in summary, we look at the measurement, a group measurement. We can describe it as the group effect plus residual. This is just one-way table. And also we define outliers. And also we can find for two-way tables. And we can always represent the cell entry by the grand mean plus row effect plus column effect plus the residual. Without residual, only get an estimate or the cell entry if the model is perfect. And here, the residual from the additive model for the two-way table measure the error and also the interactions with error, the interactions between the row and the columns. All right, and this concludes chapter 4. Thank you for watching. I will see you in our next chapter.